Hello class, this is a video tutorial on multi-stage events. In this video we'll be also learning about the multiplicative laws of probability. So let's begin. So the individual sample spaces of the events throw a coin and roll a die are, well, heads or tails for the coin, and we know that the magnitude of this is 2. And for rolling a die, the numbers 1 to 6. So there are 6 numbers to choose from in the sample space. However, if a coin and die are thrown, I want you to think about and answer the question: what is the sample space and how many total outcomes are there? You can already see here this is a misconception, but try not to read that. So if we throw a coin and a die at the same time, what's the sample space? And how many total outcomes are there? So the most common misconception is heads, tails, and 1, 2, 3, 4, 5, 6, with a total sample space of 8. However, this assumes all of these outcomes occur from one object with 8 different possibilities. So imagine this as it's called a tetrahedron. It's just an 8-sided die, labeled 1, 2, let's say 3 is in the back, 4 is there, 5 is in the back, and 6, and heads and tails. Okay, so as you can see that this is not quite throwing a die and a coin at the same time. The probability of pairs of independent events occurring simultaneously is the product of each individual event. So the probability of A and B equals probability of A times the probability of B, or you can say the probability of the intersection of A and B. This is just the same notation as this. It's the multiplication of A and B. Now, independent events, well, 2 or more events are independent if the results of one event do not affect the results of another. So for example, if you throw a coin, that has no effect over the results of what happens when you roll a dice. This is also applied to the total outcomes of both events. So for example, if we throw a coin and rolling a die at the same time, we know that the total number of outcomes in throwing a coin is 2, heads and tails, and the total number of outcomes for rolling a dice is 6, 1, 2, 3, 4, 5, 6. When we throw them at the same time, the total number of outcomes is actually 2 times 6. So the total number of outcomes of each gives us the total number of outcomes if we do them at the same time, 12. By use of a two-way table, we can properly list all the outcomes from a coin and a die throw. So for example, if we list all along the top, all the results are on the dice, and along the side, all the results on the coin, one result is 1 in the heads, 2 in the heads, 3 in the heads, 4 in the heads, and so on. Or 1 in tails, 2 in tails, and so on. We could very well easily just swap this, so have the dice go along here, and the coins go along the top. So this lists the sample space, which can be counted, which we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are indeed 12 total outcomes when you throw 2 different probabilities into the mix. The same simultaneous throw can be illustrated using probability trees. These are often used for separate event probabilities. So for example, event 1, so we can imagine this throwing the coin first, and seeing whether it lands heads and then tails, and then throw the dice. 1, 2, 3, 4, 5, 6. And hopefully you can see each of the branches has the probabilities for that one event happening. I didn't write them here because they're the same for in this example. As you can see, we should list all the outcomes that took to get here. So heads 1 is heads 1. The probability of heads and 1 occurring is half times a sixth, which gives us 1/12. Note that the sum of each probability at each stage or event must add to 1. So at this stage here, half plus half equals 1. And at each stage, this is 1, and this is another. If you add 1 in 6 for this particular stage, we get a total of 1. If we add 1 in 6 for this particular stage, we also get 1. Now, since the events are independent, the order can be reversed and still show the same results. So in this case, we threw the coin first, and then we rolled the dice. But even if we swap them, we get the exact same probability. So if we roll the dice first and then throw the coin, so when we throw the dice, the result could be 1, 2, 3, 4, 5, 6. And then for each result of the dice, when we throw the coin, it could be heads and tails for each of them. Notice how the order of this, instead of heads 1, we get 1 heads. In any case, when we multiply the probabilities of each individual event, so if we want the result of 1 heads, we get 1 in 6 times 1/2, giving us 1/12. In this particular example, the probability of all events are equal. This is not always the case. By that we mean each of these branches have the same probability, 1 in 6, as well as these ones. They all have a half. These don't always have to be the same. In this manner, it's easier to calculate multi-stage events. So for example, let's get to it. A regular coin and die are thrown. Calculate the probability of a 1 and a tails occurring. So probability of 1 intersect with tails, or the probability of 1 occurring is a half, times the probability of of 1 occurring is 1 in 6, times the probability of tails occurring is 1/2, which gives us 1 in 12. But we could just say that this is 1 tails, which we can easily find here, 1 tails, which is 1/12. Probability of 3 and heads. Probability of 3 and heads. We could go in this manner here, or because we've already drawn this, we can find it. 3 and heads, 1/6 times 1/12, 1/2, also gives us 1/12. Probability of heads and an even number. This one gets a little bit more tricky. So we want all the results that have heads. Even though I haven't written them, they're there. But we only want the ones that have even numbers there. So only the even ones. Oops. 2 in heads is even. 4 in heads is even. And 6 in heads is even. So to find all these, we have 1/12 plus 1/12 plus 1/12. So to write this out, probability of heads and even, this is the probability of heads 2 plus the probability of heads 4 plus the probability of heads 6. 1/12, 1/12, it's 1/12. That's 3 in 12, which is a quarter. Probability of an odd number. Notice how it says an odd number regardless of whether or not it has heads or tails. So going back to our probability tree, actually for this, let's actually use the two-way table just to show you that we can still use this as well. The probability of an odd number regardless of its heads or tails. So odd, odd, and odd. 1 heads or 1 tails. 3 heads or 3 tails. 5 heads or 5 tails. This is 2, that's 2, and that's also 2. That's 2, 4, 6 in total. That gives us 6 out of 12 probability of picking or rolling a odd number regardless if it's heads or tails. So the probability of odd from the two-way table is going to be 6 out of 12, which is a half. So I hope that gave you an insight into using the probability trees as well as two-way tables. I'll be giving more examples on these on our posts. Hope to see you in the next video. Best of luck.